This is Team 3's interim presentation on the analysis and redesign of a manual stapler. A manual stapler is an office tool used to fasten multiple sheets of paper together by applying a force to drive a staple down through the paper sheets and then the legs bend to secure the papers together. The estimated production volume is 150 to 200 million units annually. There are two major customer groups. The primary is office workers who have to handle large amounts of paper, and the secondary is college students for assignments and notes. The primary function of a manual stapler is to bind papers together. It does this by first storing a staple strip. Then it feeds these staples by applying a lever force and constraining the staple's movement. Then it inserts the staple into the paper by piercing the paper and then folding the legs. Finally, it assures dependability by using high-quality materials and preventing stapling fingers, and then it assures convenience by enabling an easy reload and using an ergonomic grip. There are two major assembly sequences. First is a ground-up design. It has a base body subassembly, then adds the middle supports, then adds the upper body casing. Finally, it adds the springs and then the movement subassembly. This is to minimize any sort of holding down needed for the springs while adding them into the assembly. The second design is more modular. First, it adds the base body, then all of the upper, so that the casing is done together. Then it adds the entire movement subassembly, and then finally all of the support that goes in the middle while the casing is still open.
Sequences. Sequence 2 is preferred to Sequence 1 as it has a better overall rating from its better performance in ease of transferring and handling, ease of fastening, and ease of assembling in parallel. Our function component mapping outlines what each part of the stapler accomplishes, highlighting how each part is integrated. As shown in the chart, all components are associated with two or more functions, which relate broadly to either the stapling process, stability, or user safety. The upper body, pins, springs, and staple holder play major roles in the stapling process, whereas other components, like the supports and base body, contribute to the ergonomic grip, easy reload, and preventing finger injury.
Label exploded view of the manual stapler can be seen here. It contains 15 parts, including fasteners. The bill of materials will be displayed next. The bill of materials consists of the various component materials used and their associated manufacturing processes. This includes high and low carbon steel, zinc alloy, and nylon. The associated manufacturing processes include die casting, sheet metal forming, injection molding, rolling, and coiling. The total unit cost was estimated to be $2.22. Similar products range from $6 to $20. Our product design is on the low end of the price range and is roughly 20% of the average retail price for a manual stapler.
This is the quad chart slide based on the functional importance and the manufacturing cost. From this chart, we expect a redesign of the high box, including the base body, upper body, and staples holder. This is the functional differentiation and component commonality slide. I will first talk about the functional differentiation chart shown on the left. Regardless of the customer group, the functions in the first column are necessary for operating a stapler. For the second column, only frequent staple users, such as our primary group, the office workers, will need high-quality materials and an ergonomic grip. Our secondary group, students, couldn't care less about these functions as they can just settle for cheaper alternatives or use the staplers less frequently. Next is the component commonality chart on the right. The first column labeled platform is necessary for all staplers. The second column labeled modules can be interchanged for larger staplers if the stapler needs a larger stash of staples.
Modules and common interfaces. On this slide, we show how we created two stapler variants using the same platform design. The office version is full-sized for frequent, high-volume use, while the student version uses smaller modules for lighter use. For example, the student access spring is about 25% shorter, which reduces spring force but is still enough for smaller paper stacks. The staples holder is also shortened to reduce staple capacity and material usage. Even though the module sizes change, the mounting interfaces stay the same, so both versions can plug into the same base assembly. This slide highlights the shared interfaces that make the modular design possible. Both stapler variants use the same access rod diameter and the same base body channel geometry. Only the module lengths change between versions. Because the seating geometry stays identical, manufacturers can use the same platform and assembly process for both products, which reduces cost and improves Manufacturing flexibility. Product family assembly. This slide compares the original assembly process with the updated modular assembly sequence. The shared platform components are assembled first, while the variant-specific modules like the staples holder and axis spring are added later. This supports delayed differentiation, meaning the final product can be customized near the end of the production. That improves flexibility, simplifies inventory management, and reduces manufacturing costs.